I would like now to solve for a time domain simulation. Just see how the system evolves from 0, for instance. I have to define naturally the inputs as function of time. So in this particular uOft file, which is also user defined, I get all the parameters that I need. I can also define more parameters, such as the amplitude of the alternating current component. I have those 3 inputs defined as time domain waveforms. So since these depend on time, I can simply use the time that is provided by the function, but this one is a constant value. So for it to have the correct dimension, I just say that this is this constant value times a vector of 1 that has the size of the time vector. So all of these vectors have the same dimensions. Okay, I am ready to go back to the main and consider solving for a time domain simulation. I would like to solve the MMC over, let's say, 5 fundamental periods. So I do 5 times 20 milliseconds. I still remove one time step, but you do not have to do that. This is just something that I do out of habit. And I want to see the evolution of the system from 0. I can also change the solver. Actually, for simple systems, it doesn't matter too much. For elaborate systems and stiff systems, this may have more impact. I start the system. It solved quite quickly. I see the 2 results of the Fourier analysis over the last fundamental period and over the last XP fundamental periods, XP still being defined as 3 fundamental periods. As always, the results are stored directly in the DSA time domain and harmonic domain structures, but I can also directly plot them. This time, I would like to see the set of state variables, not from the collocation method, but over the complete time span as provided by the time domain simulation. There it is. You see it starts from 0. All the variables start from 0 and then slowly converge to a steady state. Something that I can tell you at this point is that this column of strings is essentially a legend that you can specify yourself. It could really be anything, and then anything will be displayed here. I would like to compare the results of the collocation method with the last fundamental period of the time domain simulation method. I would like also to distinguish between the 2 by having the collocation results with this line style, and of course I will reduce the density of points for that particular result. So here is what it looks like. Naturally, as before, the time domain simulation have not converged to a steady state, while the collocation results are directly a steady state. There is still a small difference. So something that I can do at this point is rerun the time domain simulation from the solution over more fundamental periods, let's say over 20 more fundamental periods. Let's directly go and see the results. First, having a look at the complete time span. You see that the transients slowly disappears. It's not completely disappeared yet, but I can compare the last fundamental periods and the collocation results, which are now closer to each other. It is normal that the 2 sets of waveforms do not match perfectly, because the last time that we solved the collocation methods, we included a second harmonic perturbation on the DC voltage, which was a perturbation of 5%. Technically, we should rerun the collocation calculation without this disturbance, and then we would be able to see a better match between the 2 sets of waveforms. I can continue from here. One thing that I can mention is that we can run the collocation method not only with the numerical Jacobian, but also with the analytical Jacobian. Let's try to run this. It will not work. The reason is that before using an analytical Jacobian, you need to create the file. So let's have a look here first. MMC, single phase. We have the 4 files that are created by the user. Now if I reset the Jacobian and specifically request an analytical Jacobian, I run this code, and then there are a few more lines that are provided. Symbolic calculation of collocation Jacobian. Symbolic collocation Jacobian is calculated. Creation of collocation Jacobian function. This may take some time. And then collocation Jacobian function created. Also, it indicates that the analytical collocation Jacobian has been written at this particular location. This is exactly here. We see that a new file has just been created. I can open it. And then you understand why I automate these kinds of calculations. Essentially, these are the analytical expressions of the Jacobian. Now it has been created, and I can use the same Jacobian file for as long as I want until I bring modifications to the equations, or well, essentially that would be the main reason. If I do bring modifications to these differential equations and or to the algebraic equation, well, then I need to reset the Jacobian, in which case, if after having brought modifications in this file, I would have to set again the Jacobian reset option to 1, rerun, and then I can set it back to 0. In any case, the collocation method has just run calculations with the symbolic Jacobian and has obtained again the results. But technically for small systems, the calculation times are not very different between the numerical option and the analytical option. The numerical results, in any case, technically do not depend on the type of Jacobian that you use. Going further, I will get back to calculation of positive, negative, and zero sequences when we deal with a 3-phase system. In the meantime, I suggest we continue with linearization. Specifically, this is made in 2 steps. First, these equations defined in the equation file. So these equations are extracted from the file and written as a symbolic object. This is the first part of it. So get nonlinear system. It is done. So symbolic nonlinear system defined in DSA and LSS. This is nonlinear state space. Okay, let's have a look at that. We have a few things, and the main thing is of course the dxdt. It is the equations from the equations file, but now in a symbolic format. Those are the equations that are linearized symbolically by means of the DSA linearize function. So I can run this one. I select it, F9, and then I read in the command windows. DSA linearize symbolic calculation of linear state space matrix coefficients. This is indeed what it does, and then symbolic linearized system stored in DSA LNSS, not to be confused with an LSS. This one is for nonlinear state space, and this one is for linearized state space. Let's have a look at this particular structure. We have one field at this point. There will be more fields later on. Mat for matrices, of course. I have the A, B, C, and D matrices. A is at this point the state matrix, which is calculated as a symbolic set of symbolic variables and parameters. So this system is linearized, but it is not a numerical object. I would like to evaluate this matrix A. It is a periodic matrix. The reason is that it depends on variables that are periodic. So this is exactly what happens when I call this get 3D LTP. Specifically what it does is that it will evaluate matrix, time periodic matrix A of t, but instead of giving it as a function of time, it will give it as the set of its Fourier coefficients. F9. Okay, here again, this calculation starts with an update of the DSA structure in case numerical values have been changed in the meantime, or in case options have been changed in the meantime. Evaluation along the periodic trajectory defined in HD source, this one, which is indeed the one that is provided by the collocation results, and that is specified as an option to this LTP structure. Then the job is that we'll go from a two-dimensional time domain symbolic matrix to three-dimensional harmonic domain matrices. And this particular transformation is done for each of the four state space time periodic matrices. Now the 3D harmonic matrices are defined. We can have a look at these. DSA, they will be in the LTP field, LTP. We see the harmonic source is the one that we have requested, so we know that the matrices inside Mat are or have been calculated with this particular periodic trajectory information. The matrices are here, A, B, C, and D. They have a 3D format. You see the two first dimensions are the normal dimensions of these matrices. They have a third dimension which corresponds to the indices of their Fourier coefficients. So technically, if I want to access the index 0 Fourier coefficients of matrix A, I would take all the lines, all the columns, but only the seventh. Index 7 corresponds to the 0 harmonic rank. Naturally, if I want to access this particular matrix, I have to tell the computer where it is located. Here it is. This matrix is the 0 coefficient, is the index 0 Fourier coefficients of this matrix. Now, if I want to have the fundamental frequency Fourier coefficients, it will be index 8. How do I know that I have to check for index 7 or index 8? Well, this is just the fact that you have to map between Matlab indices and Fourier coefficient indices. If you do not know how to do that, you can also check one function, DSA functions. It's the harmonic to Matlab index with HM as a maximum harmonic index. If I say that I want harmonic index 0, then Matlab tells me this is index 7 in Matlab's language. If I want the -1 and +1, tells me that those are the 6th and the 8th Matlab indices. This is exactly the same function that is used when filling in the Fourier coefficients here. This H2i is actually the H2i with HM as maximum harmonic index.